Hey folks, we're back. I want to talk about the conservation of momentum today. So let's just dive right in. Let's consider two objects, all right? We're going to consider two objects, and they're not going to be necessarily pretty. I don't know anything about the masses' relationship to one another. All I know is I have M1 and M2, and so they're traveling, V1, V2, right? Then, at some time later, they interact, and then another time later, I see them flying off with, let's say, V2F. Maybe this is going to be I, and V1F, V1I maybe. So there is some interaction here, right? There's an interaction. There are forces at play in the interaction forces, right? And since we're only starting out, I do want to just pose this as a one-dimensional problem, only working in, let's say, the x direction, right? You can broaden this into x, y, and z. Indeed, you need to. You need to conserve momentum in every direction, as it turns out. But we're only going to show it in the x direction for now, right? Now, by Newton's second and third laws, right, I should be able to know something about this interaction here, right? I should be able to describe this. So let's do that. I can say something about the force, let's say 2 on 1. Actually, let's make this even more explicit. I'm going to say F in the x direction, 2 on 1, right? So what is the force of 2 on 1? Well, it should be equal to dpx dt. And I'm thinking about dpx of 1 dt. Again, we've dropped all vectors. There's going to be a lot of subscripts to this, unfortunately, because, again, I'm really trying to drive home that we're only thinking in one direction here. But not only that, there are two objects, an initial and a final. So there's just a lot of subscripts to kind of keep track of. We'll do our best. The next one that we can think of is fx1 on 2. And that should be equal to dpx2 dt. So you have these two forces. They should be opposite and equal. That's what we learned in chapter 8, right? That's what we've internalized now. Newton's third law tells me that I have interaction forces that are equal and opposite. So fx1 on 2 is equal to fx2 on 1. Specifically negative, right? Opposite and equal. Opposite, so different directions here. Since we're only moving in one direction, in one dimension, the negative sign is telling us that we flipped directions there. All right, let's keep going just a little bit more. I'm going to add these two up, right? I'm going to say, what is dpx1 dt plus dpx2 dt, right? Well, that should be equal to fx1 on 2 plus fx2 on 1. But we just said that these two were opposite and equal. So really what we're saying is this is equal to 0. Okay. Now I can do a little fancy derivative magic here, and I can say d dt. I can factor out essentially the derivative operator, and think about this really as an operator. d dt works on px1 plus px2. Let's just call it that. Right? And that whole thing needs to be equal to 0. So what I'm saying is this derivative of the sum of the momenta is equal to 0. The only time that derivatives can equal 0 is when they're constant, right? So what we're saying is that px1 plus px2, the sum of this, the momentum in this system, is constant. It's the only way for this to work. So the momentum in this system arc is constant. What changes is how we're distributing that momentum, right? But the momentum of these two objects has to sum to a constant value. And so this is our conservation rule, right? We have a conservation of momentum this time. And this is exactly like energy. So I can describe now an isolated system. If I have an isolated system, that means that my system is not interacting with the environment as a whole around it, right? And so now I can say delta P is equal to 0. Much like we said before that delta E, our total mechanical energy, never changed. For a non-isolated system, I can't spell today. For a non-isolated system, we're saying that delta P doesn't equal 0 now. It equals some impulse. It equals some impulse. There are outside forces. There are external forces working on this system over some period of time, right? But I'm interacting with the environment. I haven't thought big enough. If I consumed the entire environment around a system into the system, then I could truly say that momentum is fully conserved. But if I look at a very simple system, something like throwing a ball up against a wall, let's say it's a bouncy ball and it bounces back to me. Well, that wall collided with the ball. The ball went backwards, but the wall didn't, right? Now the wall is part of a bigger system, right? The wall is connected to the building is connected to the foundation is connected to the earth. Ooh, the earth is really, really big, right? So if I'm thinking about a non-isolated system, I'm probably thinking about very large systems around me, complicated interactions that are hard to kind of suss out by themselves. So we generalize it. We talk about it as an external force, an impulse, much like we talked about external works in chapter 9 and 10, right? We said for isolated systems, energy is conserved. For non-isolated systems, energy is changed by some external work from the environment. In a similar way, we're talking about momentum being conserved in isolated systems, and in non-isolated systems, momentum is changed because of an external impulse, an external force working on it. So again, momentum is always conserved. In the universe, it is always conserved. If we are calculating a non-conservation, if we are calculating a change in momentum, a net change in momentum in our system is not truly big enough to see the conservation, right? But that's okay. That's okay. Sometimes you need to worry about the practicalities of the system, right? And talk about how we can calculate certain things. And sometimes it's not worth encompassing the entire Earth into your isolated system. Sometimes that doesn't actually get you anywhere, right? So these are two different systems that we can have: isolated, non-isolated. I'm going to do a problem for our next video lecture, and then I want to start talking about the types of collisions. All right, we have generally two basic types of collisions. I do want to point out that isolated and non-isolated, they are not types of collisions, right? They are types of systems. So just kind of really keep that in the back of your mind, that when we talk about types of collisions, they are independent of the types of systems we might be working with. All right? So stay tuned for an example problem, and if you have any questions with this, feel free to drop into an office hour or shoot me an email. All right? Thanks for watching, and I'll see you in a bit.